Welcome to Physics 141 Online. I'm going to go through the first several points on this outline of material from Chapter 2, where we actually start to do physics and consider the topic of one-dimensional motion, or one-dimensional kinematics. So, where we're going with this begins with a couple of definitions. Kinematics is concerned with describing motion quantitatively. And we start off by describing and defining average and instantaneous velocity, and then average and instantaneous acceleration. But first of all, realize that what we're describing is the motion of an object, a particle perhaps, it could be a car, it could be a bowling ball, whatever. It's constrained to move along a single direction, forwards or backwards, but along just the x-axis. So it's one-dimensional motion. The average velocity, which we think of as distance per unit time, is defined quantitatively as v bar is equal to, the three lines mean it's defined this way, the change in x, delta x, over delta t. And remember that delta is the mathematical symbol that means change, which always means the final minus the initial. So if the object started at an initial time t1 at a position x1, then it moved to a position x2 at time t2, then its average velocity is simply the change in x over the change in t. Now, instantaneously, which would be the quantity that would describe at a particular moment in time how fast it's moving, not just an average velocity over an interval of time, the instantaneous velocity you would get by taking this average but moving the 2 points, t1 and t2, very close together in time. And if you could do that in such a way that those 2 points would be so close together that the delta t would approach 0, then the answer that you get in that limiting case would be equal to the instantaneous velocity. And we write it down mathematically in this limiting form, and when you study this in calculus, you will find out that we write this symbolically in the form dx over dt. The d in the numerator and denominator denotes a sort of delta, but it's actually a symbol that tells us that we're looking at a tiny change. It's a very tiny change in x with respect to a tiny change in t. And we call this the derivative of x with respect to time. Now in calculus, when we define things like this, usually there's a graphical meaning associated with it. And if we were to have a graph of position on the vertical axis plotted versus time on the horizontal axis, this instantaneous velocity would be the slope of the position versus time graph at a particular time. Then we can do much the same thing in defining average and instantaneous acceleration. So I'll move through this pretty quickly. Acceleration, in the average sense, is defined as the rate of change of velocity. Or, if we had, again, v2 minus v1 over t2 minus t1, we would do it exactly the same way that we did for the average velocity. So acceleration, since velocity would normally be expressed in units of meters per second in the International System of Units, acceleration will be in meters per second, or meters per second squared. Once again, we can have an instantaneous acceleration if we choose the 2 points, t2 and t1, to be very close together, so that in the limiting case where they approach the exact same time, we get a value for the acceleration without a bar over it. Notice that the bar refers to average in these expressions. So A, the instantaneous acceleration, is this limiting case of delta v over delta t, and symbolically we express it as dv over dt, or the derivative of v with respect to time. And once again, graphically, if we had a plot of velocity versus time, the acceleration would be the slope of the velocity versus time graph. All right, so let's now consider the very special case that often we have happening in nature for an object that's moving in one dimension but with a constant acceleration. Now this is not the way that all objects behave, obviously, but in particular, the case that we often see is an object that's released from rest and then it falls down towards the earth. So it's falling in a single direction downward, and it just turns out that on the surface of the earth, objects that are released from rest move because they're attracted by the earth with a constant acceleration. So one of the applications of this one-dimensional motion with constant acceleration will be to consider objects that are moving freely under the influence of the Earth's gravity. But before we get there, let's just think of constant acceleration motion in general. If acceleration is the slope of a graph of velocity versus time, then constant acceleration means a constant slope. And so here's a graph of velocity versus time, a straight line with a positive and constant slope, right? A straight line means it's got a constant slope. Now, a horizontal line is a special kind of straight line that would have a slope of 0, right? But what we have here is a general case of a description of motion with constant acceleration, and we're plotting velocity versus time. If the vertical axis crosses the horizontal axis at a time t0, or t equals 0, then we would say that the velocity value there would be v0. So it's the velocity at time 0. We label that on the graph. The general equation of a line, when we have a y versus x, would be, of course, y equals ax plus b, where a is the slope and b is the y-intercept. In this case, instead of y, we have v. Instead of x, we have t. And so, for the graph shown above, we would have an expression for v as a function of time that would be equal to the slope times the time plus the intercept, right? And that is exactly what we see on the graph. A, the acceleration, is the slope, so v is equal to slope times time plus the constant, which represents the value of v at a time t equal to 0, the initial velocity. And the way we normally write this is to put the constant first. And so in your physics book you'll see the very first equation that quantitatively describes constant acceleration motion is v at some time t is equal to the initial velocity v0 plus at. That's an important equation. So what it allows us to do, of course, is if we know the initial condition, if we know how fast the object is moving at time t equals 0, and if we know what the constant acceleration is, then we can predict what's going to happen in the future. We can say at a time t equals 5 seconds, how fast will the object be moving? And that's one of the important goals in our study of motion. We can also use this same kind of a graph to find the position at any later time t. And this is very cool because we not only want to know how fast it's moving at a particular time, we also want to know where it is along the x-axis. So how does this work? Well, this relies on the insight that when we have a graph of velocity versus time, that the area underneath the curve from t equals 0 to some general time t is equal to the change in position that the object experiences between those two times. Now, how do I know this? Well, for the moment, just consider the simple case. What if this line were horizontal, right? If this were a horizontal line, then the area underneath it would simply be the initial velocity times the time. And it would be an object moving with a constant velocity if the line were horizontal. And it makes sense that for an object moving at a constant speed, that the speed times the time is equal to the distance traveled, or the displacement. And so we don't have exactly that situation here. We have an object whose velocity is increasing. But the principle is still the same, that the area underneath the velocity versus time graph is always equal to the change in the object's position. And this is true even if the velocity versus time graph is not a straight line. That's one of the things that calculus allows us to do, is to find the area under curves even when they don't have this simple functional form. But the case of constant acceleration motion is really nice because we can easily calculate this area underneath the velocity versus time graph. All we have to do is take that irregular shape and break it down into two pieces that have familiar shapes. So the red line here divides the total area into a rectangle, the lower half, and then a triangle. And I know, and you know, how to calculate the areas of rectangles and triangles. So the height, the only thing we need to realize is that this additional height term is AT. And I know it's AT because the equation of this line, V, equals V0 plus AT. So at a time t, the line has increased from its original velocity value by an amount equal to the acceleration times the time. That's how far the increase has accumulated, starting from V0 to the V final at that time. And of course, the horizontal distance here of that red line is just the time t. So, very simply, the total area underneath that curve is given by the area of the rectangle, and that's V0 times t. That's easy, right? V0 is the height, and t is the base. But then we have the area of this triangle, and the area of a triangle is 1/2 the base times the height. So the height being AT, the base being t, 1/2 AT times t gives us 1/2 AT squared, so that delta x, or the final position minus the initial position, is equal to V0 times t plus 1/2 AT squared. And this can also be written, we can either write it as delta x equals V0t plus 1/2 AT squared, or we can call it x minus x0, just to emphasize that it's really the change in position that the equation is giving us. I put a little red box around this because this too is an important equation. So, combining the two results, the one that we got for v as a function of t, and now the one that we have for position as a function of time, combining these in different ways gives us additional useful equations. And I'll just summarize what those are here in closing this presentation. So for one-dimensional constant acceleration motion, the first equation is the one that we got by plotting v versus t and realizing that that's a straight line. The second equation is the one that we got by finding the area under the v versus t graph. And these two equations give us a great deal of predictive ability. If we know the initial velocity and we know the acceleration, then give us a time and we can calculate for you with these two equations how fast the object's moving at that time and what its position is at that time. Of course, we also have to know where it started, what the value of x0 is. Now, let's combine these equations. One way to do it would be to solve for t in equation 1 and plug it into equation 2. And I will skip the algebra and just show you what the result is. The result is an equation that does not have time in it. And this is very useful for problems where we don't have any information about the time. It tells us that v squared minus v0 squared is equal to twice the acceleration times the change in x. And one could write the quantity in parentheses as delta x if one wanted to. Another way to combine those equations would be to solve for a in the first equation and substitute into the second equation. That would give us an equation that would relate the velocities, the positions, and the times, but would not have acceleration in it. And that can also be a useful expression. It tells us that at a given time t, the final velocity plus the initial velocity, half of that, or the average of those two velocities, times the time, gives us the change in position. And there's a last equation that we can derive from the first two by doing yet one more kind of substitution. We can solve for v0 in the first equation and plug it into where v0 is in the second equation. And if we do that, we'll have an equation that has everything else in it but no v0. And so it looks a little bit like equation number 4, it looks a little bit like equation number 2, only instead of v0 we have v, and instead of a plus there's a minus. This fifth equation is not often used by itself, but it does exhaust all of the possibilities of combining equations 1 and 2. So this is a pretty comprehensive list of the toolbox that you have at your disposal in trying to understand motion problems in one dimension when the object is undergoing constant acceleration motion. So let me just pose a problem which we will work out in class. But I wanted you to think about using this framework of problem solving that our textbook calls the IDEA method. So here's a case. An airplane lands at the airport at a speed of 300 kilometers per hour. It's moving pretty fast when it hits the runway. The plane then decelerates because the pilot hits the brakes, at a rate 4.5 meters per second squared. And the question is, what is the minimum runway length for this plane to land safely? So there's a specific, very important question that you would have to answer in order to know whether a plane like this that has this initial speed and has this braking ability would be able to land safely on a particular runway. But before solving the problem, we want to go through this idea process. I for interpret. All right, what kind of a problem is this? It's a one-dimensional motion problem. All right, which means that I'll be able to use the constant acceleration equations to solve it because I'm told that the plane is decelerating at a constant rate. What am I given? Well, the numbers that are provided here in this problem statement need to be translated into specific symbols. In other words, the plane lands with a particular speed. That's not the final speed. That's, in this problem, the initial speed that it has. Then we're given the acceleration. It's called a deceleration, which tells us something about the sign associated with that. And those are the two quantities that were provided, unless there's additional information that might be hidden somewhere in the problem statement. But that's what the interpret step is all about. What kind of a problem is it? What quantities am I given? Now develop a plan, right? Usually this begins with drawing a sketch to show what the system looks like in the initial state, in this case when the plane lands, and then to show what the system looks like at the very end when it has landed safely, and we have to think about what that means. Once we have a sketch, we can now look at the equations that are available to us and see which ones might be helpful in solving the problem. What am I trying to solve for? I'm trying to solve for a length or a distance for the plane to land safely. So I need to pick equations that, among other things, have that distance in them. Finally then, evaluate. We want to solve for the unknown, in this case the length that the plane is going to take to land, but we do this at first symbolically. We only use the symbols that are in the equations. We don't rush to plug in numbers. We wait until we have solved for whatever the symbol is that represents this runway length. Then once we get that solved for, we're ready to plug the numbers in. But we don't just plug in the numbers, we also carry along the units. And you can see in this problem there's going to be a challenge because one of the quantities is given in terms of kilometers and hours. The other one is given in terms of meters and seconds. So there will be some degree of unit manipulation or unit conversion that we will have to do in this problem. Okay? And finally, though, in the evaluate step, we then plug in the numbers and units and we get our final answer, which in this case should be a distance, probably something that we want to calculate in meters. And the final step is assessing the answer. First of all, are the units correct? When we plugged in the numbers and the units into our equation, did the units cancel in such a way that I ended up with an answer that had proper units? If it's a length I'm looking for, hopefully I end up with units that are appropriate for a length. And finally, does the number make sense? In this case, if we got an answer for this runway length of 10 meters, probably we would say, you know what, that sounds like it's a little bit too small. Is a plane reasonably going to be able to stop in 10 meters? No, not if it's initially moving this fast. So that wouldn't be appropriate. On the other hand, if we got an answer that would be 1,000,000 meters, we might ask ourselves if that makes sense. And probably one or the other of those two extreme answers would indicate that we had made a mistake somewhere and we should go back and check our work. So that's the purpose of the assess step. If the answer seems like it might be reasonable, then we probably would judge that we're done and move on to the next problem. So we will tackle this problem in class, and I hope that this introduction to material from Chapter 2 has been helpful. If you have questions about it, it would be great for you to raise those in class when we meet next. That's where I'll see you.